angular velocity, torque, and the moment of inertia. These are the key concepts of rotational mechanics that we've learned in the previous tutorial. But how do we actually use them for rigid body rotation? Stay tuned because today we're going to implement a rigid body component in our physics system. Here's a high-level view of the entire process. The user initializes the rigid body object using all the parameters of a point mass. In addition, the user specifies the shape of the rigid body and its parameters. In this video, we will only implement a box, but it is very simple to expand it to other shapes, such as spheres and cylinders. From the shape of the rigid body, we calculate the moment of inertia tensor, basically a matrix. Using the force and the point where it is applied, we calculate the torque. Next, we rotate the inertia tensor into world space and use that, along with torque, to calculate the angular acceleration. We integrate the angular velocity and orientation and calculate a quaternion that represents the rotation of the rigid body. The quaternion is fed back into the rendering system, which translates it into a rotation matrix, which can be used to calculate the WVP matrix of the object. Most of the relevant code is encapsulated in a new class called RigidBody. The private attributes of this class include a point mass that represents the linear part of the movement. This handles the translational aspect of the object, whereas the rest of this class handles the rotation. We have a quaternion for the orientation of the object. The angular velocity is a vector that points along the axis of rotation. The magnitude of this vector is the speed of rotation. The sum of all torques in the system, also a 3D vector, a couple of 3x3 matrices, the moment of inertia tensor in local and world space. Notice that these two will be stored in their inverse form. Finally, we have the shape of the rigid body. This is an enum, and as I said, right now we only support a box shape. We have several public functions. First of all, init, to initialize the rigid body. This function takes the standard parameters that also initialize the point mass class, the mass of the object, the center of mass and the starting position, the force vector, and the void pointer to connect this rigid body to its rendering sibling. We have an additional vector called force point. This is the point where force is applied. It doesn't have to be inside the object, because the way that we need to think about this process is that there is a giant imaginary wrench whose head holds the object's center of mass and allows us to rotate the object. The rotation is determined by the force vector and the point where it is applied, which can definitely be outside the object itself. The further this point is from the head of the wrench, the greater the torque that the force generates. We discussed all this in the previous video. Notice the coordinate space where each vector is defined. The center of mass and the point where force is applied are in local space. The center of mass doesn't change, so it is easier to determine its location in local space. The point where force is applied is also easier to maintain in local space because the important thing is the vector to the center of mass. The position and force vector are in world space. After calling init, the object is still not fully initialized until we set its shape. For that, we have the next function, setShapeBox. I decided to separate this function from the previous one to make the class ready for additional shapes in the future, because every shape has its own parameters. In the case of the box, we need to specify the width, height, and depth. It is the job of the rendering system to decide what shape is appropriate for each model and the dimensions of the shape. Next, we have the update function, which is the same as in the point mass class. It takes the delta time in milliseconds and the pointer to an update listener, which allows the physics system to notify the client about the new properties of the object. To handle rotations, I expanded the function pointer with an orientation quaternion. Finally, we have ApplyForceAtPoint, which allows us to dynamically change the force and its location after the object is already initialized. The coordinate spaces are the same as in the init function. So let's see how to initialize the rigid body. First of all, we initialize the linear part of the object, which is of the point mass class. Notice that we use almost all the parameters for that, except the point where the force is applied. This parameter is rigid body specific, and we use it in the next function call, ApplyForceAtPoint. As I said, this function can be called dynamically during runtime, whenever there is a change in the forces in the system, and we also use it here as part of the initialization. This function calculates the radius vector from the center of mass to the point where force is applied. However, we need the radius vector in world space, whereas the center of mass and the point where force is applied are in local space. Therefore, we call the function local to world on the two variables to transform them to world space. This function creates a rotation matrix from the quaternion, rotates the input vector, and adds the position of the object in the world. We can now do a cross product between the radius and the force vector, both in world space. The result is of course torque, and we accumulate it into the vector that holds the sum of torques. Now let's see how to initialize the shape of the object as a box. The main job of this function is to calculate the inertia tensor. You can find many sources for the formulas of common shapes, for example, in this Wikipedia page. The values that you see here go into the diagonal of the matrix. The rest of the matrix is filled with zeros. This is a special case when the shape is symmetric around the axis. Our box is symmetric with respect to the coordinate system, so this is okay. This assumption is very common in most game engines because it is fast, stable, and accurate enough for gameplay. So what we need to do is to raise the width, height, and depth to the power of 2, sum them up as follows, multiply by the mass of the object, and finally divide by 12. This is exactly what happens in the original equation. The result is the inertia tensor in local space. As you shall see, we actually need the inverse matrix for that, so we calculate it and store it in a class attribute. The local version isn't necessary any longer, so we don't keep it. Finally, we are in the update function, which is called by the physics system on every frame. We start by propagating the call down to the point mass member of the class. Notice that we set the update listener pointer to null. We will take care of the listener at the end of this function after the orientation is updated, so we don't want to do this twice. The job of the linear member is just to update the position of the rigid body. Next, we call a private function to update the inverse of the inertia tensor in the world. First, we need the orientation in matrix form. Again, we use the GLM function 2mat3, which converts a quaternion to a 3x3 rotation matrix. The orientation quaternion rotates the object from local to world space, so R is now a matrix which transforms a vector from local to world space. In the next line, we use the tensor transformation law to transform the inverse of the inertia tensor from local to world space. This may need a bit of background. We know the torque equals the inertia tensor times the angular acceleration. The first two variables are known, and we need the acceleration to integrate the velocity. So we want to multiply the inverse of the inertia tensor by the torque. The inertia tensor tells us how resistant the body is to rotations around different axes. The inverse of this tensor tells us the opposite, how responsive the body is to torque. Both the inertia tensor and its inverse are expressed in the local coordinate system of the object. But torque is calculated in the world coordinate system, and we want the acceleration to be expressed also in the world system. To handle this correctly, we conceptually start by transforming torque into the local coordinate system by multiplying it by the transpose of the matrix R. Remember that R is a transformation from local to world, so its transpose is from world back to local. We can now multiply the result by the inverse of the inertia tensor to get the acceleration in local space. Finally, we multiply by the original R to convert the acceleration back into world space. Instead of doing these 3 steps every frame, we multiply the combination of R times the inverse of the inertia tensor times the transpose of R and save it as the inverse of the inertia tensor in the world. This combination is known as the tensor transformation law and is a well-known concept in linear algebra used for change of bases of coordinate systems. Now that we have the inverse of the inertia tensor in the world, we can multiply it by the torque and get the angular acceleration. This guy is multiplied by the delta time and the result is accumulated into the angular velocity. The next step is to create a quaternion from the angular velocity. This is very simple. The scalar part is 0 and the remaining 3 components are the angular velocity. By the way, this quaternion is also known as a pure quaternion. The next line is the classic formula of computing the quaternion time derivative for angular motion in rigid body dynamics. We multiply the current orientation quaternion by the angular velocity quaternion and scale it by a half. This gives us the instantaneous rotational change. But notice that this expression is time independent, so we multiply it by the delta time to make it time dependent and accumulate into the orientation quaternion. Finally, we normalize the quaternion. This is the new orientation of the rigid body. If an update listener was provided by the client, we notify it about the new position from the point mass part of the body and the new orientation. In my implementation of the listener, I can simply set both of them into the scene object. Somewhere deep inside my renderer, the GLM function metForecast is called on that quaternion to generate a standard 4D rotation matrix. This rotation matrix can be plugged into any transformation chain as usual. Integrating the rigid body class into the physics system is very simple. I've added a vector of this class in the private section of the physics system. Same as what we did with point masses. When initializing the physics system, we specify the number of rigid body elements that we plan to support. To allocate an element, we call alloc rigid body. Works the same as alloc point mass. We can now allocate and initialize a rigid body object in our demo and apply some initial force to it, in addition to gravity. This time the object rotates around its center of mass, which is roughly its head. Notice how the rotation is affected by changing the point where force is applied, even though the force itself remains unchanged. The further this point is from the center of mass, the higher the rotation speed. And that's it for today. Thank you for watching and I will see you next time.